You're about to find out something that is going to completely blow your mind. Scientists just discovered something that should not exist. Something so shocking that it is forcing us to rethink everything we thought we knew about the universe itself. In February 2023, astronomers using the James Webb Space Telescope made an announcement that sent shockwaves through the scientific community. They found galaxies, but not just any galaxies. These were massive, blazing, bright galaxies shining from a time when the universe was just a baby. We are talking about galaxies that existed only 500 to 700 million years after the Big Bang. To put that in perspective, if the universe were a person living to 80 years old, these galaxies would have formed when that person was only about 10 months old. That is insanely early. Now here is where it gets wild. According to everything we know about physics, about gravity, about how matter clumps together in space, these galaxies should not exist. They are too big, too bright, too mature. They contain billions of stars already fully formed and shining brilliantly across the cosmic void. Some of these galaxies are nearly as massive as our own Milky Way, which took over 13 billion years to build itself into what it is today. But these ancient monsters, they did it in a fraction of that time. The scientists who discovered them had a name for these cosmic rule breakers. They called them universe breakers. And that name is not just catchy, it is accurate. These galaxies are literally breaking our models of how the universe is supposed to work. Imagine spending decades building a detailed theory of how galaxies form, testing it against countless observations, refining it with supercomputers and the brightest minds on Earth. And then one day, a telescope shows you something that says, "Nope, you are wrong." That is exactly what happened. So what makes these galaxies so impossible? Well, let us rewind to the beginning. Right after the Big Bang, the universe was a hot, dense soup of particles. No stars, no galaxies, just hydrogen, helium, and a whole lot of energy. Over millions of years, gravity started pulling this gas together into clumps. Those clumps grew denser, hotter, and eventually ignited into the first stars. Those stars grouped together into the first galaxies. But this process takes time, a lot of time. Current models predict that early galaxies should be small, dim, and primitive. They should be like cosmic toddlers, barely learning to walk. But the galaxies Webb found, they are not toddlers. They are Olympic athletes. They are fully formed, packed with stars and shining with a brightness that our models say they should not have reached for billions of years longer. One of the galaxies discovered contains as many stars as the Milky Way, but it is 30 times more compact. Imagine cramming our entire galaxy into a space just a fraction of its size. The density, the energy, the sheer amount of matter packed into such a small region so early in cosmic history is mind-boggling. And here is the kicker. These are not just a couple of weird outliers. Webb found 6 of these massive galaxies in its first observations. 6. That means this is not a fluke. This is a pattern. This suggests that the early universe was far more active, far more dynamic, and far more violent than we ever imagined. It was not a quiet nursery where galaxies slowly and gently assembled over eons. It was a cosmic construction site on overdrive, cranking out massive galaxies at a pace that defies our understanding. But why does this matter? Why should you care that some galaxies formed a little earlier than expected? Because this is not just about galaxies. This is about the entire story of the universe. Every calculation we make about cosmic history, every prediction about dark matter, dark energy, the expansion rate, the formation of structures, all of it is built on assumptions about how galaxies form and evolve. If those assumptions are wrong, then everything downstream from them might be wrong too. We might be missing entire pieces of physics that we do not even know exist yet. Think about it this way. Imagine you are trying to solve a jigsaw puzzle. You have been working on it for years. You have most of the pieces in place and you are confident you know what the final picture looks like. Then someone walks in and hands you a handful of pieces that do not fit anywhere. Pieces that seem to belong to a completely different puzzle. That is what the James Webb Space Telescope just did to cosmology. It handed scientists pieces that do not fit, and now they have to figure out whether they have been building the wrong puzzle all along, or if there is a bigger, stranger picture they have not seen yet. Some scientists think the answer might lie in dark matter. Maybe dark matter behaved differently in the early universe. Maybe it clumped together faster than we think, allowing galaxies to form more quickly. Others believe we might be witnessing the effects of supermassive black holes that formed incredibly early, pulling in gas and triggering rapid star formation around them. There is even speculation that we might need to tweak the fundamental equations of cosmology itself, adjusting the way we calculate the expansion of the universe or the behavior of gravity on cosmic scales. But here is the thing, nobody knows for sure, and that is what makes this so exciting. For the first time in decades, we are staring at data that genuinely surprises us, data that challenges the foundations of what we think we know. The universe just showed us that it is older, denser, more complex, and far more mysterious than we ever dared to imagine. And this is just the beginning. Webb has only been operational for a short time. Every new image it sends back has the potential to reveal more impossible galaxies, more cosmic puzzles, more hints that reality is stranger than our theories predict. So the next time you look up at the stars, remember this. You are looking at light that has travelled across unimaginable distances and unimaginable time. Light that left galaxies when the universe was still in its infancy. And thanks to the James Webb Space Telescope, we are now seeing things that should not be there. Things that break the rules, things that whisper to us that the universe is far bigger, far older, and far more incredible than we ever thought possible. And we are only just starting to listen. So how exactly does the James Webb Space Telescope see these impossible galaxies from the dawn of time? How do we look at something that happened over 13 billion years ago? The answer is going to change the way you think about light, time, and the universe itself. Here is something wild to wrap your head around. When you look at the stars tonight, you are not seeing them as they are right now. You are seeing them as they were in the past. Light takes time to travel. The light from the sun takes about 8 minutes to reach Earth. That means when you look at the sun, you are seeing it as it was 8 minutes ago. If the sun suddenly vanished right now, you would not know it for another 8 minutes. The nearest star to us, Proxima Centauri, is over 4 light years away. That means the light we see from it today left that star over 4 years ago. You are literally looking back in time. Now scale that up, way up. The galaxies that James Webb is observing are not 4 light years away. They are billions of light years away. Some of them are so distant that the light we are seeing left those galaxies when the universe was only 500 million years old. Think about that. The light has been travelling through space for over 13 billion years just to reach us. Webb is not just a telescope, it is a time machine. A real, actual time machine that lets us rewind cosmic history and watch the birth of the universe unfold right before our eyes. But here is where it gets even stranger. Webb does not see light the way your eyes do. You see visible light. The colours of the rainbow: red, orange, yellow, green, blue, violet. But that is only a tiny sliver of the electromagnetic spectrum. There is so much more light out there that you cannot see. Infrared light. And that is what Webb specialises in. Infrared is light with longer wavelengths than visible red light. Your TV remote uses infrared. Night vision cameras use infrared. And James Webb uses infrared to peer deeper into space and further back in time than any telescope before it. Why infrared? 2 reasons. First, infrared light can pass through cosmic dust. The universe is filled with clouds of gas and dust that block visible light. If you try to look at a distant star forming inside a dust cloud with a regular telescope, you will see nothing. But infrared light slips right through. It is like having X-ray vision for the cosmos. Webb can see through the dust and reveal what is hiding inside. Newborn stars, forming galaxies, planets being born around distant suns. All of it becomes visible in infrared. But the second reason is even more mind-blowing. As the universe expands, light stretches. Imagine you draw a wave on a rubber band. Now, stretch the rubber band. The wave gets longer, right? The same thing happens to light traveling through space. As the universe expands, the wavelength of light stretches along with it. This stretching is called redshift, and the farther away something is, the more the universe has expanded since that light was emitted, and the more stretched or redshifted that light becomes. Here is the thing. When those ancient galaxies emitted their light 13 billion years ago, they were shining in visible and ultraviolet wavelengths, just like galaxies today. But over billions of years, as that light travelled across an expanding universe, it got stretched. Ultraviolet became visible. Visible became infrared. By the time that ancient light reaches us today, it has been stretched so far that it is deep in the infrared spectrum. That is why Webb had to be built to see infrared, because the oldest, most distant light in the universe has been redshifted into wavelengths that our eyes and normal telescopes simply cannot detect. Scientists measure this stretching using something called the redshift value, often written as the letter Z. A redshift of Z equals 0 means no stretching. You are looking at something nearby. A redshift of Z equals 1 means the universe has doubled in size since that light was emitted. A redshift of Z equals 10. The universe has expanded to 11 times its size since that light left its source. Webb is routinely detecting galaxies with redshift values of 10, 12, even higher. That means we are seeing these galaxies as they existed when the universe was only 3 to 5% of its current age. We are watching the cosmic dark ages come to an end. We are witnessing the moment when the first stars ignited and began flooding the universe with light. Before Webb, this era was almost completely invisible to us. The Hubble Space Telescope, as incredible as it is, mostly sees visible and near-infrared light. It could glimpse hints of these early galaxies, but it could not see them clearly. Webb, on the other hand, was purpose-built for this. Its giant gold-plated mirror, over 6 meters wide, collects faint infrared light from across the cosmos. Its instruments filter and analyze that light, breaking it down into its component wavelengths, revealing the fingerprints of distant galaxies. And because it operates in the freezing cold of space, far from the heat and light pollution of Earth, Webb can detect the faintest, most ancient signals imaginable. What Webb is showing us is nothing short of revolutionary. It is revealing that the early universe was not the quiet, empty place we thought it was. It was alive, active, bursting with galaxies forming at an incredible rate. Webb has found galaxies that existed just 300 million years after the Big Bang. To put that in perspective, the universe is about 13.8 billion years old today. These galaxies formed when the universe was only about 2% of its current age. That is like looking at a newborn baby and finding out it can already run a marathon. And we are seeing them in extraordinary detail. Webb can analyze the light from these galaxies and break it apart into its spectrum. That spectrum tells us what elements are present in those galaxies. It tells us how fast they are moving. It tells us how many stars they contain. It even tells us whether they have supermassive black holes at their centers. All of this from light that has traveled for over 13 billion years across an expanding universe. It is like cosmic archaeology, piecing together the story of the universe from the faintest traces of ancient light. But here is what really blows my mind. Every image Webb takes, every spectrum it captures, every data point it sends back is rewriting the history books. We thought we understood how galaxies formed. We thought we knew the timeline of cosmic evolution, but Webb keeps showing us things that should not be there. Galaxies that are too bright, too massive, too organized, too early. Each discovery raises new questions. How did these galaxies grow so fast? What role did dark matter play in their formation? Were the first stars different from the stars we see today? Could there be entirely new physics at work in the early universe that we have not discovered yet? This is what makes Webb so powerful. It is not just confirming what we already know, it is challenging it, pushing it, forcing us to go back to the drawing board and ask ourselves if we really understand the universe at all. And every time Webb looks deeper, every time it peers further back in time, it finds more surprises waiting, more galaxies that break the rules, more evidence that the cosmos is far stranger, far more complex and far more incredible than we ever imagined. So the next time you hear about the James Webb Space Telescope, remember this. It is not just taking pretty pictures of space. It is a time machine looking back across billions of years, watching the universe when it was young, wild, and full of mysteries we are only just beginning to unravel. And the deeper it looks, the more it reveals that we are living in a universe far older, far bigger, and far more wondrous than we ever dared to dream. We saw how Webb can actually look back in time using infrared light and redshift, giving us a front row seat to the young universe. Now, it is time to zoom in on those specific troublemakers, the galaxies that should not exist at all. So let us ask a very simple but very dangerous question. What does it actually mean for a galaxy to be impossible? When scientists say these galaxies should not exist, they are not being dramatic. They mean that if our current best theories are right, there simply was not enough time, matter, or structure in the early universe to build something this massive, this fast. Yet Webb is showing them to us anyway. Under the standard picture of the universe, something called the lambda cold dark matter model, galaxy formation is supposed to be a slow climb, not a rocket launch. Tiny fluctuations in the early universe grow slowly under gravity. Dark matter clumps together first, forming invisible scaffolding. Normal matter, the stuff that makes up stars and planets and you, falls into those dark matter wells, cools down, and gradually forms stars. Small galaxies appear first, then over billions of years they merge, collide, and grow into the giant galaxies we see today. If that story is right, then the early universe should be full of small, clumpy, chaotic galaxies, dim little smudges with just a few stars, still learning how to shine. That is what many astronomers expected Webb to see when it looked back toward the first few 100 million years. But what did Webb actually find? Galaxies as massive as the Milky Way, only 500 to 700 million years after the Big Bang. Some of them may hold tens of billions of stars. That is like walking into a kindergarten classroom and finding a group of fully grown Olympic athletes sitting at the desks. These galaxies are not just a bit too heavy. In some cases, they seem to pack as much mass and stars as giant galaxies today, but inside a much smaller volume. That means they are incredibly dense, more stars per unit volume, more gravity, more extreme conditions. When astronomers measure their light, they find that these early galaxies are not faint baby systems, they are blazing. That brightness means there has been an enormous amount of star formation in a very short period of time. To get that many stars that fast, something dramatic must have happened. One idea is that the first stars in the universe, often called population 3 stars, were very different from the stars we see around us today. They would have formed out of almost pure hydrogen and helium, with no heavier elements like carbon or iron. Without those heavier elements to cool the gas efficiently, these first stars might have grown much more massive, maybe hundreds of times more massive than the Sun, and burned much hotter and brighter, but died much faster. If entire galaxies were seeded with these enormous early stars, they could have flooded their surroundings with light in a very short time. When they exploded as supernovae, they would have enriched the gas with heavier elements, paving the way for the next generations of stars. Webb may be catching some galaxies right in the middle of this extreme phase. That could help explain the surprising brightness. But it still leaves a big question. How did so much gas collect so quickly in one place to begin with? Some of the bright, compact objects Webb sees in the early universe may not even be ordinary galaxies at all. They could be what scientists call active galactic nuclei, powered by enormous black holes that are feeding on surrounding matter. When gas falls into a supermassive black hole, it heats up and glows intensely, sometimes outshining the entire galaxy around it. If black holes formed very early and grew very fast, some of the light Webb is seeing might be coming from these brilliant feeding zones. That idea leads to an even deeper mystery. Our best theories say that supermassive black holes, the kind we see in the centers of large galaxies today, should take a long time to grow. They might start as the remnants of the first giant stars, then slowly gain mass by swallowing gas and merging with other black holes. This should be a billion-year project. Yet Webb is finding signs that some of these massive black holes might already be in place. when the universe is less than 1 billion years old. So now the puzzle has multiple pieces. We have galaxies that formed too fast, stars that may have formed too efficiently, black holes that may have grown too quickly. Each of those tensions pushes on the same conclusion. The early universe was doing something that our models did not predict. This is where theorists bring a dark matter back into the conversation. In the lambda-cold dark matter model, dark matter is the main driver of structure formation. It does not interact with light, but it does interact with gravity. If dark matter clumps together, it can create deep gravitational wells that pull in normal matter and trigger star formation. If, for some reason, dark matter behaved differently in the early universe, clumping faster or forming special dense regions that could help jumpstart galaxy formation and explain these massive early systems. Some researchers have suggested that maybe dark matter is not as simple and cold as we thought. Perhaps it had more complex interactions or properties in the early universe that faded over time. Others are exploring whether the laws of gravity on very large scales might need to be tweaked. If gravity was slightly stronger or behaved differently in the past, structures could have grown more quickly. That would be a radical change, because gravity is one of the pillars of physics, but the universe does not care what we find comfortable. It just does what it does. There is also a more cautious possibility. Maybe we are misinterpreting some of the data. Measuring the mass of distant galaxies from their light is tricky. Dust, unusual star populations, and active black holes can all confuse the picture. As Webb collects more detailed spectra and as other telescopes join in, some of these candidates might turn out to be smaller or less massive than first thought. That would soften the crisis a bit, but even the more careful follow-up studies still find that the early universe seems surprisingly productive at building galaxies. The tension does not simply vanish. So, we are left in a very exciting place. On one hand, our standard cosmological model still explains a huge amount of data beautifully, from the cosmic microwave background to the large-scale distribution of galaxies. On the other hand, when we push that model into the very earliest times with the new power of James Webb, cracks begin to show. The early universe is not just a quieter, smaller version of today. It looks like a different regime where matter, light, and maybe even the fundamental laws are playing by slightly different rules. This is why many scientists say that the James Webb Space Telescope has not just taken pretty pictures. It has exposed a potential crisis in cosmology, a productive crisis, the kind that signals that we are on the edge of discovering something fundamentally new. These galaxies that should not exist are like cosmic protest signs, waving at us from across 13 billion years, saying, your story about us is not complete yet. And the mystery does not stop with galaxies themselves. They are part of a much larger structure, woven into a vast network of dark matter, and driven by an even more mysterious force that is stretching the universe apart. To really understand why these impossible galaxies exist, we have to zoom out and look at the invisible scaffolding and the unseen energy that rule the cosmos. We have seen the impossible galaxies. We have learned how Webb looks back in time. We have explored why those galaxies should not exist. Now, it is time to confront something even stranger. The universe you see, everything that shines, every star, every planet, every galaxy, all of it makes up less than 5% of what is actually out there. The rest? It is invisible, and it is running the show. Let me put this in perspective. Imagine you walk into a massive theatre, the lights are dim, you see actors on stage performing, and you think you are watching the whole play. But then someone turns on a special light, and suddenly you realise the stage is just a tiny platform. The real theatre is enormous. There are invisible stagehands pulling ropes, moving sets, controlling everything from the shadows, and in the back of the theatre there is a massive engine humming louder and louder, pushing the walls outward, making the whole space expand. That is our universe. We are watching the 5% on the stage, while 95% of reality is hidden in the dark. Scientists have names for these hidden forces. The invisible stagehands holding everything together. That is dark matter, the engine pushing the universe apart. That is dark energy. Together, they control the structure, the motion, and the fate of everything that exists. and James Webb is now giving us the clearest view yet of how they operate. Let us start with dark matter. You cannot see it. You cannot touch it. It does not emit light. It does not absorb light. It does not interact with normal matter in any way we can easily detect. So how do we even know it is there? Because galaxies are moving wrong. In the 1970s, astronomer Vera Rubin studied how fast stars orbit around the centers of galaxies. She expected stars on the outer edges to move slower, just like planets farther from the sun move slower in their orbits. But that is not what she found. The outer stars were moving just as fast as the inner ones. That should not be possible unless there was extra mass out there, mass we could not see, holding those stars in place with its gravity. Since then, we have found dark matter fingerprints everywhere. Galaxies move faster than they should inside galaxy clusters. Light from distant galaxies bends in ways that only make sense if there is invisible mass between us and them. Entire galaxies are held together by gravitational glue we cannot see. The evidence is overwhelming. Dark matter is real. It outweighs all the normal matter in the universe by a factor of 5 to 1. For every kilogram of atoms that make up stars, planets, and you, there are 5 kilograms of something else. Something dark, something we still do not fully understand. And here is where it gets wild. James Webb is now mapping dark matter in ways we never could before. It does this using a trick called gravitational lensing. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravity of that object bends the light, just like a lens bends light to focus an image. But the bending tells us how much mass is there, including the dark matter we cannot see directly. Webb has observed massive galaxy clusters and measured how they warp the light from galaxies behind them. By analysing those distortions, scientists can create maps of where the dark matter is concentrated. And what those maps reveal is stunning. The universe is not a random scatter of galaxies. It is organised into a structure so vast and intricate that astronomers call it the cosmic web. Imagine a three-dimensional spider web stretching across billions of light years. Galaxies are not scattered randomly. They sit along glowing threads called filaments, with enormous empty voids in between. At the intersections of these filaments, where multiple threads meet, you find galaxy clusters, the densest regions of the universe, and holding this entire web together, providing the scaffolding, is dark matter. Dark matter formed this web. In the early universe, tiny fluctuations in density, small ripples in the fabric of space, grew under gravity. Dark matter clumped together first because it does not interact with light or normal matter. It just pulls. Over hundreds of millions of years, those clumps grew into vast filaments. Normal matter, the gas that would eventually form stars, flowed along those filaments, like water running along cracks in pavement. Wherever dark matter was densest, galaxies formed. The cosmic web is not just a structure, it is a record of how gravity has shaped the universe over billions of years. Webb is now imaging this web in unprecedented detail. It can see galaxies along these filaments forming and evolving. It can trace how gas flows from the voids into the filaments and then into galaxies. Some scientists even believe that the properties of dark matter itself might be encoded in the shapes of early galaxies. If dark matter is made of certain particles, it might behave like a wave on very small scales, smoothing out structures and making early galaxies look more elongated. Webb is testing these ideas right now. But dark matter is only one piece of the puzzle, because while dark matter pulls everything together, there is another force doing the exact opposite. Dark energy is pushing everything apart, and it is winning. In 1998, astronomers made one of the most shocking discoveries in the history of science. They were studying distant supernovae, exploding stars that act as cosmic distance markers, expecting to measure how much the expansion of the universe was slowing down due to gravity. But the data showed something completely unexpected. The expansion was not slowing down, it was speeding up. The universe is accelerating. Something is pushing against gravity, driving galaxies farther and farther apart at an ever-increasing rate. That something is dark energy. Here is the thing. We have no idea what dark energy actually is. It is the biggest mystery in all of physics. The The best explanation we have is that it is a property of space itself, a kind of energy that exists everywhere, even in the emptiest voids. As the universe expands, more space gets created, and with it, more dark energy. That energy pushes outward, accelerating the expansion. Dark energy makes up about 68% of the total energy in the universe. Dark matter makes up about 27%. Everything else, all the stars, planets, gas and dust, all the stuff we can actually see, that is less than 5%. Think about that for a second. We live in a universe where we do not know what 95% of it is made of. We are like ancient sailors who could see the surface of the ocean but had no idea what was underneath. Except in this case, what is underneath is not just unknown. It is actively controlling the fate of the cosmos. And here is where things get even stranger. When scientists measure the expansion rate of the universe using different methods, they get different answers. This is called the Hubble tension. If you measure the expansion rate by looking at the cosmic microwave background, the afterglow of the Big Bang, you get one number. If you measure it by looking at nearby supernovae and distant galaxies, you get a different number. And the difference is not small. It is big enough that it cannot be explained by measurement errors. Something is wrong. Either one of the measurements is flawed in a way we do not understand, or the universe does not expand at the same rate everywhere, or our entire model of cosmology is incomplete. Some scientists think the solution might involve dark energy changing over time. Maybe it was weaker in the early universe and grew stronger as the universe aged. Others think we might need new physics, modifications to general relativity, or new particles we have not discovered yet. The Hubble tension is one of the hottest topics in cosmology right now, and the data Webb is collecting about early galaxies, about how structures formed, about the distribution of matter and light in the young universe. All of that is feeding into this debate, because here is the deeper question. If dark matter and dark energy control the universe, and if our models of them are incomplete, then everything we think we know about cosmic history might need revision. Those impossible galaxies Webb found? Maybe they are not impossible at all. Maybe they are just the first clue that dark matter behaved differently in the past, or that dark energy had a different role in the early universe, or that there is something else, something even stranger, hiding in the data. The cosmic web connects it all. The dark matter scaffolding, the dark energy expansion, the galaxies threading through space like beads on invisible strings. Webb is mapping this hidden architecture. It is revealing the bones of the universe, the invisible forces that shape everything we see. And the more we learn, the more we realize how little we truly understand. So as we stand here, staring into the depths of space, we have to accept a humbling truth. The universe we see is just the tip of the iceberg. Beneath the surface, in the dark, there are forces and structures and mysteries that we are only beginning to uncover. And those mysteries are not just abstract puzzles for scientists to solve. They are the foundation of reality itself. They determine whether the universe will expand forever, whether galaxies will drift apart into cold isolation, whether new structures will ever form again, and ultimately, what the fate of everything will be. We started with impossible galaxies. We learned how to see back in time. We explored why those galaxies break the rules. We discovered the invisible forces holding the universe together and tearing it apart. Now it is time to zoom out to the biggest picture of all, the full scale of everything, and the question that haunts every human who has ever looked up at the night sky. Are we alone? Let me give you a number that is almost impossible to comprehend. The observable universe is 93 billion light-years across, not 13.8 billion, even though that is the age of the universe. 93 billion. How is that possible? Because space itself has been expanding. While light from distant galaxies has been travelling toward us for billions of years, the universe has been stretching, pulling those galaxies even farther away. So the edge of what we can see is not 13.8 billion light-years away. It is more like 46.5 billion light-years in every direction. Double that, and you get the full diameter, 93 billion light-years. Let that sink in for a moment. Light, the fastest thing in the universe, would take 93 billion years to cross from one edge of the observable universe to the other. Except it never could, because the universe is expanding faster than light can travel across it. The edge is unreachable, not because of distance, but because of the very fabric of space itself stretching faster than anything can move through it. We are trapped inside an expanding bubble, and we will never see beyond it. What lies outside? We do not know. Maybe more galaxies, maybe infinite space, maybe something else entirely. We may never find out. But even inside this bubble, the scale is staggering. The observable universe contains an estimated 2 trillion galaxies. 2 trillion. Each of those galaxies holds tens of billions to hundreds of billions of stars. Some, like our Milky Way, have around 200 billion stars. Others, giant elliptical galaxies, can have over 1 trillion. If you tried to count every star in the observable universe, one per second, it would take you trillions of years. There are more stars in the universe than grains of sand on every beach on Earth, and around many of those stars there are planets. This is where things get personal, because the James Webb Space Telescope is not just looking at distant galaxies, it is also looking at planets around nearby stars, exoplanets, worlds orbiting other suns, and it is studying their atmospheres, searching for signs of life. Webb does this by watching a planet pass in front of its star. As the planet transits, some of the starlight filters through the planet's atmosphere. That light carries a fingerprint, a spectrum, that reveals what gases are present. Oxygen, water vapor, methane, carbon dioxide. Each element and molecule leaves a unique signature, and Webb is finding water. Lots of it. On multiple exoplanets, Webb has detected water vapor in their atmospheres. In 2023, it found water vapor, sulfur dioxide, and even silicate clouds on an exoplanet called WASP 107b. That planet is a hot, puffy world, nothing like Earth, but the fact that we can analyze its atmosphere in such detail is revolutionary. Webb has also found hints of water vapor around rocky planets, worlds that might be more like Earth. These are not Earth-like conditions. Many of these planets are too hot, too close to their stars, or too massive. But the presence of water, a key ingredient for life as we know it, tells us that the building blocks are out there. Some exoplanets Webb is studying lie in what scientists call the habitable zone, the region around a star where temperatures might allow liquid water to exist on a planet's surface. Liquid water is crucial. It is a solvent, a medium where chemical reactions can happen, where complex molecules can form, where life, at least life like ours, can emerge. Webb is analysing the atmospheres of these worlds, looking for biosignatures, gases that might be produced by living organisms. Oxygen in large quantities, for example, is hard to explain without life. On Earth, almost all the oxygen in our atmosphere comes from plants and photosynthetic bacteria. If Webb finds a distant planet with oxygen, methane, and water vapor all at once, that could be a smoking gun. But here is the thing. Even if we find signs of life, even if we detect an atmosphere that screams biology, we will never visit those worlds. Not in our lifetimes, not in 1,000 lifetimes. The nearest star to Earth, Proxima Centauri, is over 4 light-years away. With our current technology, it would take tens of thousands of years to get there. The exoplanets Webb is studying are hundreds or thousands of light-years away. The light we are seeing from them left those planets centuries or millennia ago. If there is life there, we are seeing it in the past, and by the time any signal we send reaches them, we might not even exist anymore. That is the cruel irony of the universe. It is vast beyond comprehension, filled with trillions of galaxies, countless stars, and potentially billions of habitable planets. But it is also so big and so empty that we may forever be isolated. The distances are too great, the timescales are too long. We might be surrounded by life, by civilizations, by worlds teeming with biology, and we might never know. Or if we do find out, it will be through light, through faint signals carried across the void, whispers from worlds we can never touch. And yet, we keep looking, because the search itself changes us. Every time Webb images a distant galaxy, every time it detects water vapor around an exoplanet, Every time it peers deeper into the cosmic past, it reframes our place in the story. We are not the center of the universe. We are not even the center of our own galaxy. We are on a small rocky planet, orbiting an average star in the outer arm of a spiral galaxy, which is just one of 2 trillion galaxies in the observable universe. We are cosmically insignificant, and that is beautiful. Because despite our smallness, we are the ones asking the questions. We are the ones building telescopes that can see across billions of light years. We are the ones piecing together the story of the universe, from the Big Bang to the formation of the first stars, from the birth of galaxies to the possibility of life on distant worlds. We exist in a universe that is older, bigger, stranger, and more wondrous than anything our ancestors could have imagined. And we are just getting started. Think about what we have learned in just the last few years. The James Webb Space Telescope has shown us galaxies that should not exist, rewriting the timeline of cosmic history. It has revealed the architecture of the universe, the dark matter scaffolding and dark energy engine that control everything. It has mapped the atmospheres of distant planets, bringing us closer than ever to answering the oldest question of all. Are we alone? We do not have the answer yet, but we are closer than we have ever been. And every new discovery raises more questions. If galaxies formed faster than we thought, what does that mean for the rest of cosmic evolution? If dark matter and dark energy are more complex than our models predict, what other surprises are waiting? If we find life on another world, will it be like us, or something completely alien, something beyond our imagination? The universe is not done surprising us. Every time we think we understand it, it shows us something new, something impossible, something that forces us to go back to the drawing board and rethink everything. That is the nature of science. It is not about having all the answers. It is about asking better questions. And right now, thanks to the James Webb Space Telescope, we are asking the best questions humanity has ever asked. So where do we fit in all of this? We are a species on a single planet, looking out into the vastness, trying to understand our origins, our place, our future. We are made of atoms forged in the hearts of ancient stars. We are the universe looking back at itself. And for a brief moment in cosmic time, we get to witness the grandeur of it all, the blazing galaxies, the swirling cosmic web, the distant worlds that might harbour life. The light we see tonight left those distant galaxies billions of years ago. Some of those galaxies may no longer exist. They may have collided, merged, or faded into darkness. But their light is still travelling, still reaching us, carrying stories from the ancient past. And when we look up, when we see that light, we are connecting with something far bigger than ourselves. We are part of a cosmic story that began 13.8 billion years ago and will continue for trillions of years to come. That story is still being written, and we, impossibly small, impossibly brief, are part of it. We are the ones turning the pages, uncovering the plot twists, marvelling at the mysteries. The universe just got bigger than we thought, older than we imagined, stranger than we dared to dream, and we are only just beginning to understand it. So the next time you look up at the stars, remember this. You are looking at the past. You are seeing light that has travelled for years, centuries, millennia, or even billions of years to reach your eyes. You are witnessing the universe as it was, not as it is, and somewhere out there, in the vastness of space, on a planet orbiting a distant star, maybe someone or something is looking back, seeing our sun as it was long ago, wondering the same thing we are. Are we alone? We do not know yet. But thanks to the James Webb Space Telescope, we are closer than ever to finding out. And whatever the answer is, it will change everything.